fun. Excited about your talk too. So without any further delay, over to you, Liam, who'll talk to us about Coulomb excitation and other wonderful things.
Hello, I hope you can hear me. You probably can't see me yet because I didn't manage to get Zoom.
We can certainly hear you, sir. That's all right.
Let me see if I can get Zoom to come back to life. 1 second, sorry. Yes. Okay.
There we go. We just need your talk now.
Yeah, apologies. I'm using two screens and it's terrible.
Here we go.
Work out which screen you can see. Okay. Can you now see the correct screen?
We certainly can, Liam.
Okay.
Fantastic.
Thank you. So yes, thank you very much to Nico for organising and getting everybody together. It's quite a lot of people from around the world, and it's. I know he's been trying to get me to come to TASTE for a couple of years since we worked together at ISOLDE in 2017, I think. So it's been a few years, and it's taken a pandemic to get me to virtually to South Africa. So hopefully we can carry on in the future, and I can come and visit. So, like you said, Mark, I've had a nice introduction, so I won't actually be giving too much of an introduction myself to the topic here, because Peter also already told you about octupole deformation. Magda mentioned it. Magda also nicely introduced the Coulomb excitation and the different methods. And as we just heard at the end, there's also a bit of a hint towards future potential to do the types of things Magda was talking about, but also with radioactive ion beams. So I'll try to motivate using some experimental data why that might be of interest going forward and why it's a line that we'd like to pursue. I'll also try to keep to time. Okay, so like I said, I won't do much of an introduction, but I thought this was worth bringing up just to say, if we're measuring about, we're talking about measuring shape, what are the best nuclear observables to do that? Now, I will be focusing on octupole shapes. It seems to be a little bit of a theme in this session. Basically, the key spectroscopic observable that we want to look for here is the BE3 in order to determine the magnitude of this octupole shape. So the BE3 has some pros and some cons. Pros that, well, it's insensitive to single particle effects. So this means versus, for example, BE1 values, which are more traditionally used as a first look towards octupole deformation. And then we can say it's more like a direct measure, and you can link it to deformation, of course, using model assumptions and the comment from Peter's talk as well. Of course, you have to capture all of the E3 strength, and if you have fragmentation to different K states, excitations to different K bands, then that will also start to influence what you see. So that's why I give this Q3 linked towards the beta 3 to give you the shape. But of course, you need to capture everything in this Q3 in order for this model assumption to work. So that's not always the case. Only in deformed systems do we expect this to be true. But luckily, like I said, you're expecting very collective E3 transitions strengths when you have a deformed nucleus. So traditionally, it's difficult to access these, and as Magda said, the best way to do this is coming from the ground state using an excitation probe rather than a decay probe, which has the problems that Magda has just mentioned with various lifetimes and branching ratios being dominated by E1 decay, for example. So this Coulomb excitation method is the go-to method to measure BE3 values, and also inelastic scattering, which I'll come back to later in the talk. So the two regions of interest, the main popular regions of interest where these effects are expected to be strongest, Peter mentioned before. So he talked about the region around 224 radium, the actinide region, and I'll talk about the region around 144 barium, the so-called lanthanide region. So these are the two regions. Now, what's important to note, you see all the points where the blue lines cross, so you have something like doubly octupole magic nuclei. They're all far from the value of stability, and they're all radioactive nuclei. So the techniques that Magda talked about would have to be adapted. This is why Coulomb excitation is currently the go-to. So that's what I'll mention first. So just a quick point out of 144 barium specifically. You see the rotational band here, slightly deformed, intermediately deformed nucleus, and you see the negative parity band here, the octupole coupled band, and it looks quite nice in terms of the interleaving, and this is what you might expect from the energy levels, that you have some octupole collectivity. So whether it's really a static deformation or a vibration, that's definitely open to discussion, and maybe we'll touch on that. But what I wanted to say is the mean field theoretical calculations also, as you'll see, experimental efforts have also been focused a lot on the barium chain in this particular region. And 144 barium is the candidate you see that has the deepest minimum from many of these calculations. Of course, there's quite a few. I'll show some references in a little while. But you see that 144 barium is really the focus that everybody looks towards to see this strongest effect of the octupole definition. So, as I said, experimental efforts have also been going on, and first to the measurement was the guys at Argonne National Laboratory using Chico and Gratina, and beams produced by Caribou, the spontaneous fission source there. And they were able to measure 144 and 146 barium using Coulomb excitation. And this is the spectrum that they were able to observe. So there's a couple of things you will notice. This is 144 barium. You'll notice that the B3 value has quite large uncertainties. And this is because a couple of things is that the cross-section to populate this state is relatively small compared to, for example, the even spin states, which is a particular problem in this region of the nuclear chart versus, for example, the actinide region of the nuclear chart, where Peter showed you earlier some beautiful spectra with negative parity states populated with very large relative intensities. But here now you're starting to see it's quite in the background. You also have some contamination from isobaric or A over Q contamination. And you get a large peak to background, and you have to have very, very good gamma ray resolution, which fortunately they did with Gratina in order to even pick out the peak from the background. So we thought, maybe can we do better? Is there ways to do better? So this is the what Marcus Scheck from UWS, his question, and he went to HIE-ISOLDE and got some beam time to try to do these measurements at ISOLDE using the ISOLDE beams. Again, Peter briefly mentioned ISOLDE, and there'll be some talks about that tomorrow about the facility, so I don't go into the details about the beam production, except to say that we had a very successful experiment with 142 barium, and we also have data on 144 barium. And if anybody was at the ISOLDE workshop last week, they will have also seen Karina Henrich present the 142 xenon, which is also which is also a very, very nice data set. So there's some interesting results to come out of that. So we have managed to do like a mini campaign within HIE-ISOLDE, with HIE-ISOLDE beams to measure these octupole deformed nuclei in the lanthanide region. What I'm showing you here on the right-hand side, Peter touched on it earlier, that you can separate the data by angular range, so by the scattering angle of the particle. So now you see a few different angular ranges. This is increasing in the center of mass angular range, or rather decreasing in the center of mass angular range for the for scattering off a lead target here for the barium case. And then in the green, you see scattering off a nickel target. So we was able to do it with different targets as well, which helps to disentangle the different excitation pathways. So we basically have 4 semi-independent measurements. And this allows us to look at the cross-section as a function of angle and as a function of Z of the scattering. So Michael showed how that could be important. And we can see this peak of interest sticking out just above the background. But of course, this is quite a difficult thing to see. And one thing I wanted to show, in particular, is if you look at the sum spectrum, it becomes a bit more obvious if I put some labels on the other peaks that you see. So there's not very much contamination observed in this spectrum, actually. There is some isobaric contaminants coming, but it's not dominant. However, these peaks at higher energy are actually coming from barium-142. And you see the gamma band is strongly populated, as you might expect in Coulomb excitation, in fact. And these, even the third 2+ state is populated to a much stronger degree than the negative parity states. And these actually then there are some small branches which decay into the negative parity states, which gives you feeding, which changes this intensity. And that intensity is just coming from the feeding of this. So it's not involved in the excitation process. So you have to consider all of these effects. When these peaks become so much larger than these ones, you really have to look into the feeding, and that's a contributing effect. And that has to be somehow subtracted, if you like, or factored in, which is increasing the uncertainty all the time of this B3 that we're trying to measure. So these experiments are particularly challenging in a lanthanide region with Coulomb excitation. So what I wanted to show before I move on to addressing that challenge is just a little bit on the theory in the barium isotopes. I said it's been the focus experimentally and theoretically so far. And there's a lot of, so these are the 2 data points from argon, you see with the relatively large uncertainties. And I've just added on our preliminary value that's not yet published of barium-142. You see that, the theories have some scatter, and the data seem relatively consistent, but they all have large uncertainties. So really, to start drawing conclusions, I think we need to be a bit more precise in what we're measuring. So this is now the whole region, so not just the baryons, but also the neighboring isotopic chains. So I show all the experimental data that is currently available. And what you see is, there's the 2 barium here in red, again, have quite large error bars, but what you're able to see if you just remove, there's our new data point. If you just remove the error bars and you draw general trends, not a good experimental thing to do, but let's just do it for now. You can see there's a kind of general trend where this Q3 value, so this octupole moment, which is basically just related to the matrix element by the Clebsch-Gordan coefficient, you can see this general trend that the Q3 value is increasing with Z. So that's not necessarily unexpected. The fact that Z goes up, then the charge distribution magnitude might also increase. So that could be explained simply scaling with Z, but there is some structure here around n equals 88 where this octupole enhancement is expected to be observed. So this is, you see some structures, samarium goes down afterwards, also gadolinium goes down afterwards, but there's clearly something that we want to try to look at. But going back, the error bars are also very large. This is where the precision comes in. One isotopic chain that's kind of missing a lot of data here is the cerium isotopic chain, which sits somewhere in between. And this is something that we've tried to address. So there's a beta decay campaign. In 2018, we did a series of beta decay experiments in this, also using fast timing to try to look at some of these states. If the lifetimes are long enough, maybe we can also use the lifetime method here. So that's in the cerium isotopes. And also potentially we could look to doing this at ISOLDE as a letter of intent to develop these beams at ISOLDE. But considering all I said about Coulex and whether it's really a great technique and whether you can get precision, maybe there's another technique to be more precise in this B3 value. So this is the DD prime spoiler that we've been pointing towards a little bit with the comment in the last talk. So this was a bit, I'll skip this, but this was just a bit more of a comment I added in after Peter's talk, where there was the discussion about these alignments, and where you can see clearly that basically all of the barium nuclei, they don't really behave like the radium nuclei in terms of the alignments. They all still tend to be around alignment of 3 units of angular momentum. So that's, I think, basically the data in this region is not really consistent yet, or there's not enough data yet to start drawing conclusions on whether we have real permanent deformation like we do in the actinide region, because we'd hope to have multiple observables pointing in the same direction. and they're not all yet pointing in the same direction. So I think there's still a discussion ongoing about this, and about having consistency of the picture, and I think that's important to preface in any of the arguments that we make or conclusions that we're drawing. Okay, so this was mentioned. Peter mentioned it in the comment about the 226 radium DD prime here that you can see from the Danish, which was done with a radioactive target. So this was a 226 radium target, which is 1,600 years half-life. So here you could do this in basically exactly the same way that Magda presented with the magnetic spectrometer. You can do elastic scattering using deuterons, and you can very, 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 very nicely see the 3- state. Okay, the ground state and the first 2+ state here is scaled by a factor of 100. So you can imagine that this is still relatively small compared to the ground state, but it's there. It's definitely there compared to, for example, the E4 transition to the 4+ state, and it sticks up nicely above the background. So this is an enhanced cross section for a collective transition, and you can get very nice separation from other states, and this will give you a beautiful B3 value, if you like, and it did, in fact. Gadolinium was also done. So this is 6 MeV per nucleon, or 12 MeV deuterons, and this is at a single. I show here just one angle, so a kind of backwards scattering angle. And again, you see very nicely the 3- state, and now this is 152 gadolinium that's in the lanthanide region. What I will say again, just to always undermine myself slightly about wanting to measure these things, that already back then in the 60s, when there was the discussion about this large collective E3 and about what that means, whether it means really strongly deformed octupole transitions, etc. They were already drawing some caution here about the conclusions. So to draw conclusions concerning the nature of negative parity band from the transition rate alone is not possible. So we see this often, that we try to look at this BE3 and see if it's enhanced, and I'm guilty myself. And an enhanced BE3, you can start to draw conclusions that you have permanent or rigid octupole deformation. We need more parameters. We need a broad range approach to looking at these nuclei. Okay, so can we do inelastic scattering with radioactive ion beams? So we can't make a target. We have to do this with the beam, so inverse kinematics. And HIE-ISOLDE is where these beams are available with the strongest intensities and the cleanest, free of contamination. So this is where we want to do it. Miniball Peter showed you already, and what I want to show you is this new setup at ISOLDE, the ISOLDE solenoidal spectrometer, which is now on the 2nd beam line from HIE-ISOLDE. So a solenoidal spectrometer versus conventional inverse kinematics reactions basically allows you, now this is an example of a transfer reaction, but to give you the impression, what you can basically do is translate the energy in the center of mass frame proportionally to the energy in the lab frame. And you do this in the solenoidal field because you're basically, you have these like kind of shifts, and you have cyclotron motion of the ejectiles from the reaction. So this is a very nice technique. It was developed using with the Helios spectrometer, the first of its kind, about 10 years ago at the Argonne National Laboratory. And we wanted to do that and bring that to CERN with radioactive ion beams, and that was the birth of the ISOLDE solenoidal spectrometer. And the trick is you basically you resolve this, and it becomes directly proportional into Z, and then this Z is also proportional directly to your scattering angle. So it very, very nicely resolves your kinematics, even when you're inverse, when you have the heavy beam on the light target. Instead of having this compression at larger angles, you have just a linear relationship. So it really resolves the spectrum, and it allows you to take advantage of reactions, very, very inverse kinematics reactions. So to do that, you need a big solenoidal magnet. So that's, this was the project led by the University of Liverpool before I was there actually, by Robert Page, and well, a UK-led project also with the University of Manchester in Daresbury, STFC Daresbury. And they were able to source, with the help of collaborators at Argonne from Helios, were able to source an MRI magnet from Australia, from the University Hospital in Queensland. So we were able to purchase that from the hospital, really take the wall down from the hospital, get the magnet out, ship it halfway across the world, and then finally bring it on truck to CERN, cool the magnet back down, test it, it worked, thankfully, and then we were able to deliver it inside of the ISOLDE hall. So this is, you can see a couple of photos of it being brought into the ISOLDE hall before it was placed on the beam line. And here it is now next to Miniball. That was in February 2017. By the end of the year, we'd managed to build up some magnetic shielding. And you see here at the back, there's some diagnostics box. We actually ran beam through with the magnetic field on, and we tested everything worked. It worked wonderfully. So that was the status in November 2017. And then the year after, in September 2018, we were able to have everything installed inside in order to make these reactions. So a target array, various different detector systems, and we could move everything inside and make a very large vacuum chamber. So now we have our experimental chamber, but we didn't have any silicon detectors. So this was the project at the University of Liverpool to build and construct this array, a hexagonal array, 6-sided array of double-sided silicon strip detectors. And what you see here is 4 silicons wafers down each side, so 24 in total, and each of these wafers has 128 strips. So you really get very, very precise 1 millimeter precision measurement of your Z position of where these protons interact with your array. This was built and delivered finally to CERN in August 2019. But in the meantime, in 2018, I said, we had this kind of setup, but the array wasn't ready. We had a very nice collaboration with the friends from Argonne and Helios, and they were able to lend us their detector array and data acquisition. So I won't tell you about the details, but the publication is here. It was published earlier this year. This is the first measurement using the ISS, really demonstrating that it works. And you can see that CERN news were quite happy about it as well. So we're ready to go with this, and we have the new detector now. This is where the status earlier this year, when we had grand plans for this summer for commissioning the detector. So in February, we put it inside, and so now it sits inside still, of course. COVID-19 means we weren't able to travel as freely during the summer, so sitting there waiting, but we're now setting up to do remote alpha tests. So Bruno is on the line. He's helping us as the local person, and we're trying to get things up and running to do the commissioning remotely. So we're making progress even in these times. So I think I have about 4 or 5 minutes left. So I just wanted to motivate. I've mentioned this device because I realized that nobody else at this conference, I think, is talking about the ISS. So I wanted to advertise it a little as well, but show you what we can do. So Magda told you a lot about this. I won't have to repeat that, thankfully. But using the cross sections, we can get out deformation lengths or B3s, if you like, whichever type of model assumptions you want to use from inelastic scattering. So not purely Coulex, but now inelastic scattering using deuterons. And you see the cross section to kind of answer Georgi's question is also in the millibar range. Now, if we're able to do this analyzing in the solenoidal field, we can cover quite a large center of mass angles. Now, you'll find if you do the kinematics that the deuterons are going forward from this. What I showed you before is the target in the upstream array, where everything goes backwards. That's very easy, for example, for DP reactions, because all your background channels are going forward as well. So when you look in the backwards for DP, you're essentially background free, or very, very, very low background. And if you make coincidences with recoils, for example, then there is no background. But as soon as you want to measure something, a reaction going forward, you've got a lot of reactions now going forward. So you're going to have to pick out the reaction of choice somehow. So that then becomes the challenge. So analysing the deuterons going forward, we can cover, well, actually slightly lower, probably from about 15 to about 40 degrees in the centre of mass. And you can see these are the angular distributions for 146 neodymium. And we're able to cover really the peaks of the 3- state. We can change this angular range simply by changing the position of this target relative to the silicon array. So we have full choice over this. But we're going to have to pick out the reaction of choice. So the idea to do that is to detect the recoils. But of course, they're all going essentially at 0 degrees. So that's going to be difficult. So that's where the ionization chamber comes into play. So we're going to detect, instead of using silicon detectors, we're going to use an ionization chamber at 0 degrees and try to pick out the elastic scattering recoils. So the other reactions you might see, of course, you get transfer, multi-nucleon transfer or few nucleon transfer, fusion, particularly we're using deuterated polyethylene targets, which has carbon inside. So you also get fusion with the carbon. And these will all give you slightly different signals in your ionization chamber. Also, time of flight, time difference between the deuterons or charged particles hitting your detector array and the ionization chamber will also help. And so by doing this, we hope to be able to pick out the reaction. So this was the purpose of a proof of principle experiment that we did at Helios. So this was led by Ben Kay. So very grateful for him for getting this up and running. Original plan was to use 146 neodymium, but we couldn't get that beam, so we used xenon. Unfortunately, the cross-section for exciting any of the states in xenon, as you might know, especially 136 semi-magic nucleus, quite low. So what we were able to do is actually show elastic scattering, which is this line. And you can also see, if you look carefully, this is energy versus Z. The Z position is essentially angle. You can also see angular distribution coming through here in the intensity. And so, I mean, this was a proof of principle. We showed that you can do it. There's very low background. We don't see any of the excited states, but really the background is very, very small. And you really can pick out the elastic scattering, and most likely then, of course, the inelastic scattering. So that's what we want to do. We didn't do it yet. We hope to do it either next year. There's a deadline for new proposals to go to the ISOLDE solenoidal spectrometer collaboration in a couple of days. So I'm working on this proposal right now. We hope to submit the proposal. And this just shows you what you can do with 142 barium as an example. So just default resolution around 50 keV. Okay, if it was 100, 150, or even 200 keV, you could still really likely perform these experiments with. You see, the 3- is very well separated. So these are the states we expect to populate in roughly the cross-section ratios. There are other candidates that we'd like to do, maybe xenon. So these are the isobars, and also 144 cerium. So these are the ideas that we're going to go forward with for the next INTC. Okay, so thank you very much. I just wanted to thank all the people that you can see on the slide that have all contributed to getting to this stage. So thank you very much.
Well, thank you, Liam. Exciting stuff there. We're looking forward to all the results in the future. And you may have seen we're over 500 participants, not in this session. We're 150 for this session, 500 in total. So it's going global, folks. Couple of questions. Musha has a question. Over to you.
Yes, Liam. I have to admit, it's been quite a while, me thinking about this problem, and maybe Peter can chime in. But concerning the electromagnetic transition, I seem to recall that if you have permanent octupole deformation, then there is a certain ratio between the B of E2, B of E3, and B of E4. And if they follow this particular ratio, they will distinguish between octupole deformation and octupole vibration. Again, it's been quite a while since I thought about this problem, and maybe Peter can chime in. Is that correct?
I'm not so sure. I think if you really want to start going into isotope by isotope and looking at, I think it's probably not a good estimate. I mean, it might be a good rule of thumb, but we're starting to see now that the mean field models are able to give you quite some precision on the electromagnetic moments, and they're providing quite a bit of variation. So maybe within some simplistic model that might be the case, but I think we're reaching the point now with the measurements that we have to start being much more precise than that.
Well, thanks, Liam. Georgie has a question.
Yes, thank you very much, Liam, for the very nice talk and for the thoughts about what one could do with DD prime. But I suppose when you are talking about DD prime reaction, then you would think about a deuterated polyethylene target. Is this what you have in mind?
Yes, exactly. To start with, we want to use deuterated polyethylene, and that's predominantly the reason why we want to do DD prime, because the targets are simple. But yes, so for example, in the future, you could think about a gas target, removing the carbon, which would help with recoil detection. And it would also open up the potential to do alphas for alpha prime as well, which would be another probe.
Well, that's what I was my way of thinking. Actually, maybe the DD prime is not the best if you're trying to look for Coulomb excitation. So getting anything which is high in that certainly might help better. So this might be, yeah, if gas or liquid targets might be available, that can make the things look a bit differently. If that's an option that one can think about.
Yeah, our astrophysics friends are really very interested in gas targets. So I would be hoping to piggyback a little bit on their developments, help them out a little, and yeah, in the future, if gas targets are available, I think that would definitely help. Here with the DD prime, we're strongly influenced by the nuclear component as well. So we do have to, of course, consider that, and that will be a model uncertainty that comes into the experimental value.
But if we get your point is that if we have the cross sections comparable to the transfer reactions, then what you get as beam intensity and count rates for transfer reactions, you should get at least the same, if not better, for the Coulomb excitation. So any beam on which you could do DP, for example, we should be able to do DD prime as well and get with similar statistics. Is this correct?
Yeah, that's pretty much the way we're going. Yeah.
Okay, thanks.
Sounds good. And Liam, the folks with other questions in the chat there, Liam, if you could address those offline, because we are running a little bit late and
yeah,
we need to go to the next exciting contribution or component in the taste, or the next the next serving, if you like. And but before I hand over back to the head chef, I would like everybody to unmute themselves and thank all our wonderful speakers in this marvelous structure section. Thank you. And
Also,
with
Mark,
that,
you go,
the head chef, here we go. Nico, over to you.
Thank you so much, Mark. And I apologize for not introducing you before. You are one of the old tasties here coming to South Africa regularly. And we appreciate those spinning tops you brought last time from Florida, I guess. Unfortunately, those are finished. And now I have to do the same experiments with boiled eggs, hard-boiled eggs, which sometimes is more difficult, but still you can see the change in the angular momentum, right? So thank you so much, Mark, for your contribution and from being part of the taste one more time. Thank you so much. Another round of applauses for Mark. Okay, so the next session